All right, let's start. Number 8, the wow signal. On August 15, 1977, astronomer Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University, scanning the sky for signals at frequencies near the 1420 megahertz hydrogen line, the frequency astronomers had long theorized an intelligent civilization might use to broadcast into space, because hydrogen is the most abundant element in the universe, and any technologically sophisticated species would know this. He was doing a routine review. He was not expecting to find anything. He found something. A narrowband radio signal appearing in the data printout, varying in intensity over the 72 seconds the telescope was pointed at its source, in a pattern consistent with a signal coming from a fixed point in the sky outside the solar system. The signal was strong, more than 30 times the background noise level. It was in the correct frequency range. It displayed the expected rise and fall intensity profile of a signal from a star-fixed source drifting through the telescope's beam. Amon circled the printout in red pen and wrote in the margin, "Wow." It has never been detected again. Dozens of attempts to reobserve the source region, including a 1995-1996 campaign with a telescope far more sensitive than Big Ear, have found nothing. The origin is disputed. It came from the direction of the constellation Sagittarius. No star in that direction is a strong candidate for an artificial origin. No known natural source produces a narrowband signal at the hydrogen line with that intensity profile. No satellite, aircraft, or terrestrial interference has been identified as the cause. Various explanations have been proposed over the decades: a hydrogen cloud, a cometary outgassing event, an interstellar object, and none has been universally accepted. The wow signal remains the strongest candidate for a detected extraterrestrial radio signal in the history of SETI research. It is also the only one that has never been explained. It was heard once, it disappeared. It left a margin annotation that has been reproduced in textbooks, museum exhibits, and a spacecraft plaque. Whatever it was, it has not come back. Number 7. Fast radio bursts. In 2007, astronomers analyzing archival data from the Parkes Observatory in Australia found something buried in observations from 2001, a burst of radio waves lasting approximately 5 milliseconds that appeared to have originated from billions of light-years away. It was called a fast radio burst, a label that understates how inexplicable these events are. The burst released, in those 5 milliseconds, as much energy as the Sun produces in approximately 3 days. It crossed billions of light-years of space, and it was gone in the time it takes to blink. Since then, fast radio bursts have been detected in large numbers. The CHIME telescope in Canada has catalogued hundreds of them. They arrive from apparently random directions across the sky. Most are one-time events, a single burst from a given location, never repeated. A subset, called repeating FRBs, fire multiple bursts from the same source, sometimes in patterns, sometimes at seemingly random intervals. The source of the first localized repeating FRB was traced to a dwarf galaxy approximately 3 billion light-years away. Another was traced to a magnetar in our own galaxy, confirming that at least some FRBs can originate from magnetar flares. But magnetar flares alone do not explain the full population. The energy scales, the polarization properties, the timing patterns of certain repeating FRBs, and the apparent associations with specific galaxy environments all suggest a diverse range of possible sources. Some FRBs have been observed to repeat with intervals that appear almost periodic, separated by active windows of dozens of days, followed by quiescent periods. A source that turns on and off on a schedule. Whether that schedule reflects orbital dynamics, precession, or some other periodic physical process is unknown. Several thousand FRBs have been detected. Their origins are multiple and partially understood for some, wholly unknown for others. They represent the most energetic millisecond timescale phenomena in the universe, and the complete physical picture of what produces them, and in particular, what produces the periodic repeaters with their structured windows, has not been written. Number 6. The anomalous excess of cosmic rays above the GZK limit. There's a theoretical maximum energy for cosmic ray particles that travel across cosmological distances. It was calculated in 1966 by Kenneth Greisen and independently by Georgy Ztepin and Vadim Kuzmin. The calculation is straightforward. A proton traveling at extremely high energy through the universe interacts with the cosmic microwave background photons that permeate all of space. At energies above approximately 5 × 10 to the 19th power electron volts, a threshold called the GZK limit, the collisions between the cosmic ray proton and CMB photons become energetic enough to produce pions, robbing the proton of its energy. A proton above the GZK limit cannot travel more than roughly 160 million light-years without being attenuated below the limit. Cosmic ray detectors, including the Pierre Auger Observatory in Argentina, have detected cosmic rays above the GZK limit. They are rare, but they are there, arriving from directions distributed across the sky. If these particles are protons, they should have lost their excess energy before reaching us, unless they came from relatively nearby, within 160 million light-years. But the sources in that region of sky are not obviously the kinds of violent, high-energy objects expected to produce cosmic rays at these energies. If the particles are not protons, if they are heavier nuclei, which are harder to identify and are less strongly attenuated, then the composition of the highest energy cosmic rays is itself in open question. The Pierre Auger data has provided evidence that the highest energy cosmic rays may be heavy nuclei, but the composition analysis is not definitive, and the deflection of heavy nuclei by galactic and extragalactic magnetic fields makes source identification extremely difficult. The highest energy particles in the universe are arriving on Earth, and their origins and the mechanism that accelerated them to these energies remain subjects of active, unresolved research. Number 5. The long-period radio transients. In 2022, a new class of astrophysical object was discovered, and it does not fit neatly into any existing category. Using the Murchison Wide Field Array in Western Australia, astronomer Natasha Hurley-Walker and her team detected a radio source that pulsed on a period of approximately 18.18 minutes, far longer than any known pulsar period, far shorter than any known binary orbital period relevant to this energy scale. It repeated consistently across multiple observations before going silent. In 2023, a second long-period radio transient was discovered with a period of 21 minutes. In 2024, a third was found with a period of 22 minutes and additional unusual polarization properties. These objects are sometimes called ultra-long period magnetars as a working hypothesis, but the period problem is significant. Known magnetars typically pulse on timescales of seconds, and the emission mechanism that keeps a magnetar radiating, the rotational energy dissipated as the star spins down, should not be efficient at 18-minute periods. The emission should have died long before the spin rate dropped that low. Alternative explanations have been proposed: a white dwarf binary system with a specific magnetic geometry, a highly evolved magnetar in a state not previously seen, an object of an entirely new category. Each proposed explanation introduces its own problems. The long-period transients are not rare one-off events, they're a population. Several have now been found, suggesting a class of object that has gone undetected because it doesn't fit the timescales we were searching in. The universe appears to have been pulsing at 18-minute intervals in multiple directions at radio wavelengths, and we only started listening for it in the right way recently. What is pulsing and why at this interval is not resolved. Number 4. The 1977 UHF television interference from deep space. On August 3, 1977, 12 days before the WOW signal, a different anomaly was recorded that received far less attention and has remained more obscure. The Ohio SETI program at Big Ear recorded a potential signal in the UHF range that was not at the hydrogen line frequency. This event has been substantially less studied and is not referenced in the mainstream SETI literature with the same frequency as the WOW signal. Less well-documented anomalies in the SETI data record include sporadic narrowband signals detected at Parkes, Greenbank, and other observatories, each appearing once and not repeating. More concretely documented is a signal detected in 2015 by a group of Russian astronomers using the Ratan 600 telescope in the direction of a star called HD 95128, also known as 47 Ursae Majoris, a sun-like star known to host gas giant planets, located approximately 46 light-years from Earth. The signal appeared at 11 GHz, with a strength significantly above the noise floor. The Russian team investigated it over the following year and notified the SETI Institute, which promptly organized follow-up observations. Neither the original Russian observations nor the follow-up observations from other facilities detected the signal again. The most probable explanation for this signal is a Russian military satellite or other artificial terrestrial or near-Earth source, an explanation the researchers themselves acknowledged as most likely. The Russian team filed an inquiry with the Russian Space Agency. No official explanation was published. The signal appeared once, was associated with a direction containing a nearby sun-like star, and has never been detected again from that location. Unlike the WOW signal, the 47 Ursae Majoris event is almost certainly not extraterrestrial. But its ambiguity represents something broader. We do not have the observational infrastructure to resolve brief, non-repeating anomalies. And for each incident that receives scrutiny, there are presumably others that pass through data archives unreviewed. Number 3. The anomalous dimming of KIC 8462852, Tabby's star. In 2015, citizen scientists working with the Planet Hunters project, reviewing data from the Kepler Space Telescope, flagged a star behaving in a way that no other star in Kepler's database behaved. KIC 8462852, later nicknamed Tabby's star after astronomer Tabitha Boyajian, who led the scientific follow-up, was dimming. Not in the regular, shallow, periodic way caused by a transiting planet. In irregular, deep, non-periodic dips that sometimes blocked up to 22% of the star's light. No planet, no swarm of comets, no known stellar phenomenon produced dips of that depth and irregularity in a pattern consistent with the observations. The explanation that attracted immediate public attention was a Dyson swarm, a megastructure built by an advanced civilization to capture the star's energy, partially blocking its light in the irregular patterns observed. This hypothesis was taken seriously enough and ruled out seriously enough to generate substantial scientific literature. Subsequent observations with multi-wavelength monitoring found that the dimming was wavelength dependent. It affected different wavelengths by different amounts, in a pattern consistent with dust rather than an opaque solid structure. A megastructure would dim all wavelengths equally. The dust hypothesis regained ground. But the secular dimming, the apparent overall fading of Tabby's star over timescales of years, has been confirmed by comparing photographic plates going back more than a century. The star was brighter 100 years ago than it is today. Dust can explain the short period dips. It is harder to explain a century of secular fading. Various natural explanations have been proposed: a large planetary collision producing a debris disk, the aftermath of a giant comet breakup, a swallowed planet leaving a trail of material. None has fully accounted for all the observations simultaneously. Tabby's star remains the most anomalously behaving star in the Kepler dataset. After years of observation, follow-up campaigns, and modeling, it is understood better than it was in 2015. It is not fully understood. The source of the irregular deep dips in the context of the long-term secular dimming is not definitively identified. Number 2. The breakthrough listen signal from Proxima Centauri. In April 2019, the Parkes Observatory in Australia was conducting routine observations as part of the Breakthrough Listen SETI program when it picked up something during a scan of Proxima Centauri, the nearest star to our solar system, located approximately 4.2 light-years away and known to host at least one rocky planet in its habitable zone, Proxima Centauri b. The signal, later labeled BLC1, appeared at a frequency of approximately 982 MHz, notably a band avoided by most human radio technology to reduce interference. It drifted in frequency in a manner consistent with the Doppler shift expected from a transmitter on a planet orbiting a star. The Breakthrough Listen team spent more than a year analyzing the signal before it was reported in the press. When the analysis was published, the team concluded it was almost certainly radio frequency interference, a signal of terrestrial or near-Earth artificial origin, most likely a piece of human technology producing or reflecting a signal that appeared, in the observation, to come from the direction of Proxima Centauri. The directional consistency with Proxima was likely coincidental. The frequency drift attributed to a planetary Doppler shift could be explained by other mechanisms. But the team was explicit about the uncertainty. The signal was not definitively explained. The specific source of the RFI was not identified. The analysis ruled out the signal as a reliable SETI candidate. It did not rule out all possible natural or artificial origins. The star it was associated with is the nearest star, hosting a potentially habitable planet, and the signal had several properties consistent with what a SETI target would be expected to produce. The honest conclusion was probably not extraterrestrial, source unknown, not definitively resolved. BLC1 represents the state of SETI observation at the frontier. Candidate signals with naturalistic explanations that cannot be fully confirmed, originating from the most interesting nearby targets, arriving at frequencies that demand investigation and ultimately produce ambiguity rather than resolution. Number 1. The 21-centimeter absorption signal from the cosmic dawn with an amplitude that required something we have never directly detected. In 2018, the EDGES experiment in Western Australia reported a detection that the team described with understated precision as cosmologically interesting. They were attempting to detect the 21-centimeter radio signal from neutral hydrogen in the very early universe, the signature expected from the epoch of cosmic dawn, when the first stars were igniting and their radiation was beginning to interact with the surrounding hydrogen gas. They found the signal, but its amplitude, the strength of the absorption feature, was roughly twice as large as standard cosmological models predicted. Not slightly larger, twice as large. An amplitude that large at that redshift requires the hydrogen gas to be colder than it should be, or the background radiation to be hotter than it should be, or both. The standard model of cosmology accounts for neither. One explanation proposed almost immediately after the EDGES publication was dark matter. If dark matter particles interacted with ordinary matter through a hitherto unknown force, a milli-charged dark matter model, they could have cooled the hydrogen gas at cosmic dawn by drawing energy from it. This interaction would need to be extremely weak because we have never detected dark matter interacting with ordinary matter in any other context. But it was the right order of magnitude to explain the edge's signal. The signal itself has been disputed. A competing analysis of the edge's data suggested the absorption shape was inconsistent with a pure cosmological signal and may contain instrumental systematics. A subsequent independent experiment, SARAS-3, did not confirm the edge's detection. The community remains divided on whether the edge's amplitude is real or an artifact. But if it is real, if the cosmic dawn hydrogen was genuinely colder than predicted, then something was drawing heat from the primordial gas at the moment the first stars were turning on. Something cold, invisible, and interacting that we have never directly detected, that was present everywhere in the early universe, that was cooling the hydrogen at the moment of first light. The most direct signature of dark matter interacting with ordinary matter that any experiment has ever claimed to observe was sitting in a radio signal from 180 million years after the Big Bang, detected by a small array in the Australian desert, with an amplitude that required physics we do not have. Whether it is real and whether that physics exists is still being resolved.